Hi. In this unit, I'm going to talk about contrastive predictive coding, CPC. This is a technique that's gained a lot of momentum in the last couple of years, and it's very similar to maximum mutual information training. And in fact, a lot of the theory behind this is directly tied to mutual information training. So it's very appropriate for this section. So the first thing I want to talk about is where we were in the last section. So we've got a population on a pair XY. This might be an image and this might be a sound wave. And then given an X, we're going to define something that takes X to some abstraction of X by defining a probability distribution. Given a Y, we define something that takes Y to an abstraction of Y. And we're interested in optimizing these two extractions of information such that we preserve the mutual information between X and Y, like what objects are in the scene and what objects are being described in the audio. So our objective is to maximize the mutual information between these extracted information. This might be a bag of words. And this formal objective function asks that we limit the amount of information in the extracted features or bag of words or whatever this extracted variable is. And I pointed out last time that when you're maximizing something, if you're using a variational method, you can maximize a lower bound, and hopefully the maximum of the lower bound approaches the thing you're interested in. And we can lower bound this expression by using cross entropy estimates of these entropies. And I'm going to make that a little bit more explicit this time. So this is defined to be an entropy under this distribution we're talking about. So this is the entropy. Note that in the definition of this entropy, the population distribution is the distribution being inside the log in the definition of entropy. So of course we can't compute this because it depends on the population, but we can compute a cross entropy where we replace this part with something that's completely computed by the model. This is the standard cross entropy upper bound on entropy. So we get that the cross entropy is an upper bound on the entropy, and then we replace these entropies by cross entropy estimates. These go up, so this quantity goes down, so we do get a lower bound on the thing we're maximizing. Now, the problem we have is that if we break this into parts, an entropy minus the unconditional entropy minus the conditional entropy, then we're maximizing an entropy. And maximizing an entropy goes in the wrong direction when we replace it with cross entropy. So I don't know if all of that was clear, but the bottom line is that there's another way to do things that avoids this adversarial aspect of that comes in when you're trying to maximize an entropy and you estimate it with a cross entropy. So there's an alternative way of trying to maximize this mutual information. And that's noise contrastive estimation. So this is our objective function. What we're going to do now is see how to maximize this without using the difference of entropy approximation. And this is going to give us a general, I'm going to state, I'm not going to prove, but I'll cite the proof. I'm going to state a very general method of giving a lower bound on mutual information. So if I've got two random variables, Z and W, any two random variables, as long as I can sample from the joint distribution, I can sample pairs. So I'm assuming there's a joint distribution that defines mutual information. Given only the ability to sample from these two variables, I'm going to define a contrastive task, sort of like an again. So this contrastive task is going to draw n pairs from the joint distribution. And then we're going to take these n pairs from the joint distribution, and we're going to pick one of them at random, the ith one. And then we're going to take all of the z's in a list and the ith w. And so then we're defining this new distribution where we draw the pairs at random from the joint distribution. I give you the Z parts and one of the W's, but I don't tell you which Z the W goes with. And the contrastive engine has to predict which one of these Z's was paired with this W. Okay, if you're watching this on a video, you can go back and listen to that again if it didn't make sense. So that's what we're doing. We draw n pairs, we put the Z's out, we pick the W's from one of them, we don't say which one, and we ask a discriminator to tell us which of these Z's was paired with that W. And so this becomes our objective. So this is just a bound on mutual information. So I'm going to define a discriminator loss. This is just an n-way classification problem, right? This I could be any one of these n's, so it's n-way classification. We're gonna draw this classification problem from that distribution I just defined, and then we're gonna look at the log loss or cross entropy loss, and we try to predict I, right? So there's a loss, and that loss is going to depend on our model. This model is just trying to predict I. Could be a deep network. Could be anything. And so this expectation is determined by W. W can be, you know, good or bad at this classification problem. So that phi. So there's a loss that depends on phi. Sorry, I misspoke. Phi could be good or bad. There's a loss that depends on phi. And there's a constraint in this theorem that this probability distribution has to be defined by a softmax over I. That's what we do all the time. But the score for I has to look at just Zi and W. So the score for I is just looking at the ith Z. It's not allowed to look at all of the Z's. And that's required for this theorem. And then the theorem is that the mutual information between Z and W is bounded by the log of the number of Z's there are. I should have used a capital N there. The number of Z's that there are minus the loss. So if the loss goes to 0, then we get a log n bound, which is not great, but at least it's a lower bound. And it's a lower bound that gets larger as the loss gets, as we get better at the task. So it's not clear that this theorem it's not a very powerful theorem because this log n is a very weak lower bound. But this discrimination task has proved very effective, and we'll get to that. Now, in the original formulation of information theoretic or maximum mutual information co-training, we put in these terms that try to drive down the entropy of Zx and Zy, right? Because we want to block this trivial solution. If we make Zx equal to X and Zy equal to Y, then this mutual information is the mutual information between X and Y, which is the best you can do. We want to block this trivial information by limiting the information in this abstracted information. Again, this might be the bag of words associated with an image and a bag of words associated with a sound wave. But in contrastive predictive coding, they do something else. They drop this term. So here we've got the contrastive objective function, and now I'm just looking at one direction. I'm breaking the symmetry. I'm distinguishing the X's from the Y's. And I'm looking at one of these directions. So this is the contrastive problem. I give you a bunch of ZX's, I give you the ZY, I want to know which ZX was the ZY paired with. That's the contrastive task. And this is the log loss of on that task of this model phi. And what's forcing the Z's not to be equal to, is what's forcing these to be different from just the input X, is that the classifier here that's predicting I is required to just use the inner product. For each Y and each I, it's just using the inner product of the two vectors. These are going to be vectors now in this application, in what's being used in most CPC applications now. And the idea is if you make this score just an inner product between these abstracted variables, it means these have to sort of carry the relevant mutual information on their sleeve, in the sense that it has to be linearly extractable. So whatever's being used to determine which of these ZX is paired with this ZY has to be there in a simple inner product. And that's going to make linear uses of this feature powerful, hopefully. Okay, this was the original CPC paper that introduced the acronym CPC. Here we've got a speech signal. This is going to be a completely unsupervised, an attempt at an unsupervised extraction of useful classification features. Ultimately, we would be interested in taking a speech signal to a set of phonemes. But here we're pumping the speech signal, we divide it into frames or chunks of some size. We pump it through a deep neural network, they're calling it G encode, to get a vector here. We've also got a G autoregressive that's going across the top, like an RNN, that's producing a vector that's summarizing the history. And now they want the summarization of the history to be such that it can make predictions into the future about what the sound wave is going to look like in the future. But we're not modeling the sound wave at all. We're just taking the sound wave through a network to some abstracted representation. And then we're going to look at the inner product of this vector and that vector and use that in the contrastive objective function to measure how much mutual information there is between here and here. So the contrastive objective function is going to take this CT and a bunch of Z's. One of them is this one, but others are just drawn randomly from the marginal on the Z. And the contrastive task is to tell which one of the Z's was paired with this CT. I'm just reviewing the contrastive task. So so you're optimizing the autoregressive network and the encoder network to maximize a sum over some number of steps into the future of the mutual information of this with that statement in the future. And there's a philosophical point one might want to make here, and that is, how do you define the difference between signal and noise in generality, right? I've got this, even if this is a really clean speech signal, I want to somehow separate the signal that's coming in through that speech. What am I learning by listening to it that's going to be useful? Signal, as opposed to noise, which might have to do with whether the person has a rough voice or something that's at least different information, right? So what makes something information as opposed to noise is, does it carry information about the future? So if there's something in this signal that carries no information about the future, about anything you're going to encounter in the future, that's by definition noise. So this mutual information concept provides a signal-noise distinction, and what we're asking here is that this extracts signal, and these extract signal as opposed to noise. Okay, that's a philosophical point. This is a paper, appeared in February this year. This paper got a lot of attention, and it deserves a lot of attention. This is a very significant advance in unsupervised image feature extraction. So what they do is they take a corpus, they take ImageNet, unlabeled. We're going to do unsupervised learning on ImageNet. And the way we're going to do this is we're going to take an image and we're going to take augmentations, what are known as augmentations. That means you shift the image, or you rotate the image, or you delete a piece. You can think of it as some kind of modification of that image, some transformation. It's standard in ImageNet training to take images and reflect them or translate them just to get a bigger data set. So that's called image augmentation or data augmentation. Here we're taking various augmentation methods, and we're taking an image and considering a pair of two different augmentations from the same image. Okay, so this might be a rotation, this might be a deletion of a piece. You know, you can change the lighting. There are lots of different mutations, augmentations you can define. So I've got pairs that are augmentations of the same image. So so you think of them as having the same causal source. Now you want to extract features that extract the mutual information between these two augmentations. And you just use that CPC objective that I just defined, including the scores having to be inner products. And when you do that, you get these feature vectors that that take an image and extract it to a feature vector. And you can use those feature vectors for a linear classifier. So this is a standard way of measuring unsupervised feature extraction for images. You have whatever your favorite method is that just takes the unsupervised images and extracts features. Then you take those features and see how well you can do with a linear classifier on those features, right? So this is a standard way of saying, have I extracted information that can be extracted further or used with linear operations on that vector. And so here's a plot of ImageNet top one accuracy using linear predictors on features that were trained in unsupervised way. And when this paper appeared early this year, it just completely dominated the field. It's, you know, if we're looking at a 400 million parameter model, it's competitive with a completely supervised method. So this was a big deal paper. So CPC is a really up and coming method for unsupervised feature extraction. And we'll stop there. Thanks.